this video, let us discuss about the architecture of ALexNet. So we have already come across this ALexNet earlier, isn't it? So here we are going to discuss it in a detail, and we are going to have a very good knowledge on ALexNet in this video. So we all know that ALexNet was the winner of the 2012 ImageNet large-scale visual recognition challenge. Oh, right? Okay, fine. So what we can understand from this, so let us try to understand about the ImageNet data set first. So it contains images from dogs, horses, cars, etc. And it contains 1,000 classes, and each class contains thousands of images. So in total, there are approximately 1.2 million high-resolution images. So in total, there are 1.2 million high-resolution images in this data set used by researchers for training, testing, and validating the model designed by researchers, right? So totally it consists of 8 layers, out of which 5 convolution layers, and then there are max pooling layers, and then fully connected layers, and the output layer is a 1,000 channel softmax layer, right? So the pooling used here is maximum pooling, right? So you may be, let's look into that first, like how it looks like. You can look into this output. Actually, here you can see that there are 1,000 channels, right? So here you can see some inputs, and then there are some convolutions, and then you can see some maximum pooling, and then fully connected layers also, right? So this is what I told you. And then we can see a softmax over here. Why 1,000 channels of softmax layer are taken, right? So as I told you, the ImageNet dataset contains 1,000 different classes of images. So at the final output layer, we have one node for each of these 1,000 categories, and the output layer is the softmax output layer. So we all are aware that the output, when there are multiple classes, we use softmax as the output layer, right? So this is the basic architecture of ALexNet, right? So let us look into this one. The input to the ALexNet network is 227 into 227 size. And why 3 is written over here? Because it is a RGB image, which means it is red, green, and blue, right? So then we have the first convolution layer. In that, you can see that it has 96 different kernels, and each kernel size is 11 into 11, and the stride is equal to 4. So output of the first convolution layer gives you 96 different channels or 96 different feature maps, right? And each feature map contains features of size 55 cross 55. So this is the output we have received, right? 55 into 55 into 96. Let us try to understand in detail. Here the size of input is 227 into 227, and 3 stands for the channels, basically red, blue, and green. And then you can see the convolution kernel, that is 11 into 11, and the number of kernels is equal to 96, right? And strides is equal to 4. And here there is no padding, right? So what are we getting now? 55 into 55 into 96, right? Right. So after convolution, we have an overlapping max pool layer where the maximum pooling is done over the window 3 cross 3 and stride is equal to 2. So here what we can find is, as per maximum pooling window of size 3 cross 3 and stride is equal to 2, that means maximum pooling will be done over an overlapped window. So after this pooling, the size of the feature map is reduced to 27 into 26 and the number of feature channels remains 96, right? So what is the size of the input? 55 into 55, and size of the convolution kernel is 3 cross 3 and stride is equal to 2, right? We will see the calculation shortly. And what are we getting now? 27 into 27, right? So then we have second convolution layer, which is of kernel size 5 cross 5. And in this case, we use, right? So in this case, we will be using pad equal to 2, right? We are using padding equal to 2. So the output of the convolution layer remains the same as the input feature size. Thus, it is now again 27 into 27, but the number of kernels used in this case is 256. So that means from this convolution layer output, we will get 256 different channels or 256 different feature maps, and every feature map is of the size 27 cross 27. Clear? So remember that we have used stride 1 and padding is equal to 2, right? And let us look into the next one. Now again, so every feature map after the second convolution is of the size 27 into 27. Now again, we have an overlapping max pool layer where the maximum pooling is again done over a window of 3 cross 3 and stride is equal to 2, right? Which means again maximum pooling is done over overlapping windows, and output of this become 13 into 13 feature maps, right? Right, again it is 13 into 13 feature maps, and the number of channels what we get is 256. So what was the size of the input? That was 27 into 27. Size of kernel is 3 and stride is equal to 2 and padding is 0 over here. So what do we get now? 13 into 13, right? So it's very clear, right? So every feature map after this pooling is of the size 13 cross 13. Then we have three consecutive convolution layers. You can see over here, of which the first convolution layer is having the kernel size of 3 cross 3 with the padding equal to 1 and 384 kernels. Give you 384 feature maps of size 13 cross 13, which passes through the next convolution layer. So in the second convolution, the kernel size is again 13 cross 13 with padding equal to 1 and it has 384 number of kernels. That means the output of the convolution layer will have 384 channels, or it could be 384 feature maps. And every feature map is of size 13 cross 13. So we have seen padding equals 1 for a 3 cross 3 kernel size, and that's the reason the size of every feature map at the output of this convolution layer is remaining the same as the size of the feature map which are input to this convolution layer, right? So now the output of the second convolution is again passed through a convolution layer where kernel size is again 3 cross 3 and padding equal to 1, which means the output of the convolution layer generates feature maps of the size 13 cross 13. But in this case, ALexNet uses 256 kernels. So that means at the input of this convolution, we have 384 channels, which now get converted into 256 channels. Or we can say 256 feature maps are generated at the end of this convolution. And every feature map is of the size 13 cross 13. Now the next one is overlapping max pool layer, where the max pooling is done over a window of 3 cross 3 and stride equal to 2, and that gives you the output feature maps, and the number of channels are the same as 256, right? And the size of each feature map is 6 cross 6, right? Now we have a fully connected layer, which is the same as a multi-layer perceptron, right? We have seen about the multi-layer perceptron, right? So the first two fully connected layer have 4096 nodes, which means 4096 nodes each, right? So this is basically the output of this, right? Because if you multiply 6 into 6 into 256, you'll be getting 9216, right? So after all this, we are getting 9216 nodes of features, and each of these nodes is connected to each of the nodes in this fully connected layer. So the number of connections we will have in this case is 9216 into 4096, and every node from this fully connected convolution layer provides input to every node in the second fully connected layer. So here we will have a total of 4096 into 4096 connections, as in the second fully connected layer also we have 4096 nodes. And then at the end, we can have the output layer with 1,000 softmax channels. So the number of connections between the second fully connected layer and the output layer is now 4096 into 1,000, right? So what we can see is like the ALexNet, we have seen around 1.2 million training examples. So it was big to fit on one GPU. So sometimes what was done is actually half of the network is put in one channel and the other half of the network is put in another channel. And as they are into two different channels, so that made it possible to train this network on two different GPU cards. The GPU used was GTX 583GB GPU, and the network took between 5 to 6 days to get trained. Just imagine, it took 5 to 6 days to get trained. So here they use cross GPU parallelization and all. So we will be studying this shortly, right? Fine. So now hope this is clear. Let me make it little more clear so that there won't be any doubts from your end in this ALexNet, right? So what do we see over here? We have seen that ALexNet input is 227 into 227, right? And we have seen that F is equal to 11, right? And let us try to calculate this, right? Let us try to calculate this now. So we know that if there is no padding, what is the formula? N minus F divided by S plus 1, right? So substitute this over here. Now what do we get? 227, right? 227 minus 11, right? Because F is nothing but this one, right? And this is N. Let me make it very clear, okay? So that everything will be easy to you. And you can see that S is equal to 4. So I can substitute 4 over here plus 1, right? So what is the answer now? Exactly, right? So what do we get now? 55 into 55, right? And then this is the number of filters, right? Number of kernels. So this is clear, right? So that is why we got it as 55 into 55. So this part is clear now? Okay. So let's understand this now. So this is already clear, right? So let us try to understand the next part now, right? So what do we know? Like you can see that I already told you that there is a padding for 2 over here, right? Okay. So let us try to understand here now. So what did we get from the convolution layer? So first convolution layer used was 11 into 11, 96 filters, and stride was equal to 4, right? And then pooling is applied with a 3 cross 3, and stride is equal to 2, right? And with the stride is equal to 3. Sorry, stride is equal to 2, right? This is what we have seen, right? So let us try to get that now. Yes. So what is, so let us try to get this, right? So this was clear to us. So what is N now? Right? So N is 55, right? Minus F. What is F here? 3 cross 3, right? So this is F basically divided by stride is taken as 2, right? Plus 1. So what do we get now? 52, 55 minus 3 is 52 by 2, 26 plus 1, 27, right? So we get 27 into 27 into 96. Clear? So the next step, what happens? Now the padding is done over here. So the padding is equal to 2 over here, right? So I told you when I explained the theory, right? So what will happen now when there is a padding? How does the formula change? N plus 2p minus f divided by s plus 1, right? So what is n now? N is nothing but 27, right? So 27, I said padding as 2. So 2 into 2 minus what is filter over here? F. F is nothing but 5 divided by s, right? So yes, in the sense 27, 4 minus 5 is 1. So what will be the, okay, plus 1, right? So again, what do we get? We get it as 27 into 27, right? Now this time it is 27 into 27 into 256, right? So after that, what is being done now? Yes, we are doing pooling, right? So in pooling, stride is equal to 2, right? So what will be the formula now? So the input is 27, n is 27 minus f is 3 divided by striding is 2 plus 1, right? 24 by 2, 12, 12 plus 1 is 13. So we got 13 into 256, right? Clear, right? So now what is the n now? N is 13 now. So 13 plus is padding done over here. Yes, there is a padding. Padding is equal to 1 over here, right? So padding is equal to 1 over here. So what do we get? 2 into 1 minus f is nothing but 3 divided by s. S is again here 1, right? Plus 1. So 13 minus 1, 12. 12 plus 1 is 13. So we are getting it as 13 into 13, right? Again, this will be the same because we are using the same, right? So that is why we are getting this. This will be the same. This will be the same. Now look at this here. What will happen? Stride is equal to 2, right? So 13 minus f is nothing but 3. There is no padding over here. Divided by, yes, s is 2 plus 1, right? So 13 minus 3 is 10. 10 by 2, 5 plus 1 is 6. So 6 into 6 into 256. So when you multiply this, we will be getting this, right? So clear to you? So hope this part is clear, right? So when you multiply 36 into 256, you will be getting 9216. Then we are connecting it to two fully connected layer of 4096 neurons. Then we are connecting it to the output, right? So output of 1000 neurons because there are 1000 classes over here, because there are 1000 classes over there, right? So this is what we have to understand with this, right? So hope this is clear to you. Because this when you look at an overview, this looks like complicated, but actually it is very simple to understand. If you understand the mathematics behind it, then that's super cool, right? LeNet. So we have some knowledge on convolutional neural network, and also we have come across different CNN structures. And here we are going to study about the LeNet in detail. So when LeNet was developed, that time there was no GPU to help training, and CPU was also very slow, due to which high resolution images were not used. So LeNet was trained on grayscale images, and the shape of the images were 32 into 32 into 1. That means the height and width of the image is 32 and the number of channel is 1. What is that 1? Why do we say it as 1? Because it is a gray channel image, right? So it will try to recognize the handwritten digits on bank checks. So if you look at this picture, you can different handwritten digits over here, and the model will try to recognize those digits. So this is the goal of the LeNet. So this is basically the task which LeNet perform was the handwritten digit it has to recognize. So now we will see how the structure of a LeNet looks like. Right, so you can see over here, for some simplicity, I have taken it as A. It could be any input image of size 32 into 32 into 1. So this could be this image, and this is the image of the size would be the input to this network. So this is our first, you can see over here, first convolution over here, right? So you can see that there is a change from 32 into 32 to 28 into 28, right? So this is the first convolution layer, and there you can see around 6 filters, right? And like we will be seeing this in detail. So if you look into this, we can say that here the convolution filters were 5 cross 5 applied at stride 1. Subsampling layers were 2 cross 2 applied at stride 2. So let me give you a brief introduction about it. Like, it is an excellent first architecture for CNN, especially on MNIST dataset and image dataset for handwritten digit recognition. So here 2 sets of convolutional activation and pooling layers, followed by a fully connected layer, activation, another fully connected layer. Finally, we have softmax classifier. So convolution filters were 5 cross 5 applied at stride 1, and subsampling or pooling layers were 2 cross 2 applied at stride 2. So here the architecture is like convolution, pool, convolution, pool, convolution, and then fully connected. Right? So when you look at this image, it looks like complicated, but it is not really complicated. It is going to be really easy to understand. Okay, so let me redraw this diagram so that we can be comfortable with that. So let me take the whiteboard now. So let me redraw it. Okay, so there is an input image. Okay, so now the input image goes to, so let me draw the diagram first. I'm not going to, so it is going to be convolution and 5 cross 5, and it has 6 filters. So 6 filters, I'm writing it as 6F, and then stride is equal to 1, right? After that, it goes to maximum pooling, right? So it goes to maximum pooling. So in maximum pooling, right? So in maximum pooling, what we can see is pad is equal to 0. I'm writing it as P. Pad is equal to 0 and S is equal to 1, right? And then it goes to, again, convolution. Again, it goes to convolution. And here you can see 5 cross 5, convolution 5 cross 5, and it has around 16 filters, right? It has 16 filters, and here you can see that, right? So let me correct this. So let me explain it to you. So here we have an input image, 32 into 32 into 1, right? Then we have convolution 5 cross 5, 6 filters, and stride 1. Hope it is clear. And then we have maximum pooling, and this is again 2 cross 2, and here stride is equal to 2. Sorry. So let me clear this. Right. So here the stride is equal to 2. Right. So no need to bother about padding. Here there is no padding. Right. So stride is equal to 2. Right. And then we have convolution. Right. And then in this convolution, what we have is 5 cross 5, and it has 16 filters, and then P is equal to 0 and S is equal to 1. Right. So I'm continuing with this. Then again, what is the next one? Again, it is going to be maximum pooling, and in maximum pooling 2 cross 2, and then stride is equal to 2, right? And then we have fully connected layer, right? Then we have fully connected layer, and I'll explain everything in detail to you. So don't worry about it, right? So this is going to be 1, 120. And again, we have fully connected layer. So this is going to be, right? So fully connected layer. So this is going to be again 2, 84. And then we have output, right? So output is nothing but softmax, right? So here it is 10. So let us study about this in detail. Now, if you see the input and output size of the image, and even the number of channels are different over here. Here, the size of the input image is 32 into 32, 32 into 32. So after you do this operation, it changes into 28 into 28 into 6, right? So now what is this 6? This 6 is nothing but the number of channels, right? So here you can see that it is clearly written that there are 6 filters, right? So the number of channels would always be the same to the number of filters we have used in the model, right? So we have used 6 filters. So that is why we are getting the number of channels as 6, right? And let me write size for this also. So this is become 14 into 14 into 6. So let me write this, then I will explain what is happening here. And then this convolution 10 into 10 into 16, right? And then I have 5 into 5 into 16, which is equal to 400, right? So let us discuss about this in detail. So you will become very clear about this LeNet shortly, right? So let us try to understand about this. So here in some places you can see about striding and padding and all, right? So hope we remember that what is striding. So in the first convolution layer, I have written stride is equal to 1, and second place I have written stride is equal to 2, right? So let us try to understand this in detail, right? So just look at this. What is the size of the input? Size of the input is nothing but 32 into 32 into 1, right? This is the input size, and this is fed to this convolution, right? So this is feed into the convolution layer 5, right? So this is fed into the convolution layer 5 cross 5, and there are 6 filters and stride is equal to 1, right? So now let us look into this place, like how it works, right? So this is what we are going to see now, right? So look at this now. So what we had actually input is 32 into 32 into 1, and we have used convolution, right? And convolution is 5 cross 5, right? And how many filters were used? 6 filters were used, and stride is written as 1, right? So now let us try to find out this. So what is the formula that we have seen? N plus 2p minus f divided by s plus 1, right? Divided by s plus 1, right? So the next one is also n plus 2p minus f divided by s plus 1. So let us try to understand this now. What was the input image size? That was 32. And here there is no padding. So this term goes 0 minus filter. Filter is nothing but 6 over here. Here striding is 1, right? So this becomes 1, right? Similarly, the same over here. So 32 minus 6, 32 minus, I think, yeah. So n plus 2p minus f, right? So here we have seen that this convolution is actually, this is f is 5, right? Sorry. Let me make the change now. Sorry for that. Right, so 32 minus 5, right? So this is nothing but the number of channels, okay? Number of channels, right? This is basically n, right? And this is basically F. Clear now? So 32 minus 5 plus 1. So what is the answer now? 28. Here also we get it as 28. And what is the number of channels over here? Number of channels is nothing but the number of filters. So we get the answer as 28 cross 28 cross 6. Hope it is clear now, right? So you can see here 28 cross 28 cross 6. So this we have completed now. Now what has happened? Now it is moving into the pooling layer. So what does this pooling do? It reduces the size of the image. So here what pooling we are using? We have come across two types of pooling, maximum pooling and average pooling. And here the maximum pooling is used, and you can see that it is 2 cross 2 and stride is equal to 2. So why stride is equal to 2? So that the image will get shrinked or reduced, right? So the input to this maximum pool is what? This 28 into 28 into 6, right? So let us see whether how we are getting this output now, right? So let us try to understand now. So for the second layer, what happened now? So we know the formula already. N is 28 over here, because that is the input to the pooling now, right? So 28 minus filter. So filter, what we have seen, F. I mean, I'm asking about F, right? So it is 2 cross 2, right? So F is going to be 2 cross 2, right? So 2. So 28 minus 2 divided by, yes. So what is stride over there? Stride is 2 plus 1. And here again the same, right? 28 minus 2 divided by 2 plus 1. So what is the answer now? 26 by 2, 13. 13 plus 1 is 14. So 14 into what is the number of channels over there? So let us look into that. 14 into 6, right? So that's why we are getting this 14 into 6. Now this becomes the input to this convolution layer, which is 5 cross 5, and it has 16 filters, and here padding is 0 and S is equal to 1. Shall we try to solve that now? Yes, right. So in the third layer, this is what we had. And what is the input to this third layer? That is 14, right? And it is convolution is 5 cross 5. So that becomes F, right? And so what we got in the previous case, 14 into 6, right? So let us look into that again, 14 into 6. This is what will be the output, right? So now we are using this padding is 0 over here, and stride is also equal to 1, right? So we are not going to bother about it now. So 14 minus 5 plus 1, comma, 14 minus 5 plus 1, right? So what will be the answer now? 9 plus 1 is 10. So what will be the output now? 10 into 6 or 16 now. 6 or 16 now. It is going to be 16 because the number of filters used is 16 over here, right? So what is the next step? So now this convolution is being done, right? Convolution is being done. What is the next step again? Now this is going to be maximum pooling. So what is the input now? 10 into 16, right? And stride is equal to 2, right? So 10 into 16, and this stride is going to be 2, right? So for the next layer, so this is going to be fourth layer, right? So let us discuss about this fourth layer now. So here this is again 2 cross 2, and stride is equal to 2, right? So let us substitute in the formula now. N is 10 over here, and padding, no padding, minus F. So F is nothing but this convolution, right? Divided by S. S is this stride plus 1, right? So 10 minus 2 is 8. 8 by 2 is 4. 4 plus 1 is 5, right? So what is the number of filters used? So number of filters used is 16. So what will be the output now? 5 into 16, right? So hope this is clear, right? Right. So look at the previous one now. So 5 into 5 into 16. So what will be the answer now? 400, right? So let us try to understand this now, right? So when you multiply these things, you'll be getting it as 400. What is this 400? 400 pixels. So we got 2D image and that has to be converted into one-dimensional vector, right? Now what is happening? It is fed into fully connected layer, right? It is fed into fully connected layer and you can see this 1 comma 120, right? So these 400 will go to these 120 neurons. So every neuron will process these 400 pixels, right? So this is fully connected layer and the next one is also a fully connected layer, right? So here how many neurons are used? 84 neurons are used. In the previous case, actually 120 neurons are used and here 84 neurons are used. Then it is connected to the output. So now if you look into the output, it is saying that 10, right? So why it is saying 10? Say basically like think that we are talking about the MNIST data set. So here we have output ranging from 0 to 9. It could be either 0 or 1 or 2 or 3 up to 9, right? So the total number of output possible is only 10. So how this will be selected, how the output will be selected, like based upon we are using softmax activation function over here. It will calculate the probability for each number like 0 or 1. For whichever probability is the maximum, that will be considered as the output over here. So what is happening here? The actual image is 32 into 32 into 1 and that is reduced to 5 into 5 into 16. So this is reduced to this, right? So 2 dimension to 1 dimension is passed through the fully connected layer and then to the output layer. So this is how the LeNet architecture work, right? So hope it is clear to you, right? Right? So first it has input and it had 2 convolution layer, 2 fully connected layer, 2 pooling layers and 1 output, right?